Good morning, everyone.
Good morning, doctor.
All right, thank you, Avni. Morning to you. So today we are going to into a new chapter, which is chapter 5. All right. Okay then. Now chapter 5 is on hydraulic structures. That means we are going to learn about typical hydraulic structures that is typically used in um, practice, all right, in real situation. We are not going to learn all about the all hydraulic structures, only the common ones, all right. Mm, Now, at the end of this chapter, you are going to, learn a couple of hydraulic structures, and then you also will be able to estimate discharge over through all these structures. And then the final topic is on stealing basin. So you will learn how to design stealing basin, especially this USBR stealing basin type 3. USBR actually stands for United States of America Bureau of Reclamation. Right. Now, hydraulic structures, it could be artificial or natural structures, which can be used to control uh, flow of fluid, lah, right? Now, the structures can be made of a range of materials, lah, such as rocks, concrete, timbers, tree trunk, and so on. Um, sometimes, right, due to animals, for example, beaver, right? You have fallen trees across the river. All those are considered, obstruction or structures obstructing the flow, and you can actually use it to control the flow as well, lah, basically. Now, one of the hydraulic structures. One of the hydraulic engineering works is to design and analyze hydraulic structure lah. Hydraulic structure is constructed to control flow, maintain water level. If you said maintain water level, for example, you have sluice gate, weir. You can also control maintain water level lah. Control erosion. In terms of if you are using stealing basin, then you can control erosion. Or others lah. Examples of hydraulic structures are sluice gate, spillway, weir, energy dissipator, and constrictor. In our topic, in our chapter, right, we are going to look at sluice gate. We are going to have some calculation as well. Theoretically, we are going to look at spillway. And then we are also going to look at weir with calculation. And then finally we are going to do some design lah using based on the energy dissipator structure concept that we have learned. The top two images are the sluice gate. Okay, it's used to control. For example, if you look at the figure on your left, right, you can also maintain the water level, all right, behind the sluice gate. And then this is sluice gate as well. It's for irrigation purposes, all right. Or it could be, such as tight gate. That means you control flow in and out from the river mouth, All right. The bottom two figures shows the weir. We have looked at this weir before, eh? All right, the labyrinth weir. And then you have on the top here are weirs as well. On the left is sharp crested weir. The crest is sharp, eh? It's actually later we'll see. When I said sharp, how are you going to define sharp? It's actually based on the thickness of water flowing over it, compared to the thickness of the crest of the weir itself. You can actually classify it into whether it's broad crested or sharp crested, right? Um, for example, here you have on your right, you have three types of weir. You have solid weir, you have broad crested, you have crumb weir. This is known as crumb weir. The broad crested, when the thickness of water, all right, um, if go over it, all right, if it's if it if the thickness of the crest is 60% or more, then the thickness of the nap, all right, which is water thickness of water that goes above it, you can classify it as broad crested. Okay, so this is H, the thickness. If you look at this, the H is actually the height of water measured from the crest of the weir, to the top surface. All right. So if you look at here, this is H. All right, which is measured from the top of the crest. Top of the weir to the water surface. Now the height of the weir, we have the symbol of P, or use P to denote the height of a weir. This is suppressed. This is contracted rectangular weir. When I said suppressed, right, that means the width of the opening of the weir is as wide as the channel's width. When it's contracted, right, it could be contracted like it. For example, here you have both sides being contracted. Sometimes only one side is being contracted. So you have, in this case, when it is contracted both sides, because it's being contracted, right? Here, no contraction, right? So it's a price. Here, n is equal to 2 lah, because it's contracted on left and right. If it's one side, then n equals to 1. We are going to learn about that in the topic of weir. Then you have stilling basin. There's different type of stilling basin. This is one type. This is another type. Now, this type is known as USBR type 3. Okay, USBR stilling basin type 3, where you have tube blocks, buffer blocks, and also end sail. This is what we are going to design: the height, the width, the spacing, all right, and then the distance, how far you are going to place them from each other. This is what you would know how to do. Do the calculation at the end of this topic. Okay, let's look at the first hydraulic structure, the sluice gate. Sluice gate is used to control and measure rate of flow. For example, you have sluice gate at the dam structures. It is used to control. You have sluice gate. At the top of the weir as well. All right, where you can control the release lah of the water. When it is full, you want to release it, right? For example, there are cases in Sungai Klang or Klang Dam cases where they have to release the water because normally dam is actually designed based on the height of water upstream or behind it. If it's too much of water, the pressure is going to be too high, then you have overturning of the structure, which is dangerous. That's why they have to release it lah. Okay. Now, this is sluice gate. The direction of flow is from left to right. Behind the sluice gate, you have water. All right. In this case, water, right? With the height of y naught. Right. This is the depth of water behind sluice gate. And then um, you could have hydraulic jump. You could. Sometimes there's no hydraulic jump if this is submerged. That means this depth, right, is, it actually submerge all this. All right. So you don't have hydraulic jump. Now, in case of hydraulic jump, okay, you have a depth of y1 upstream of hydraulic jump and depth of y2 downstream of hydraulic jump. Now, we have learned this depths, which is known as conjugate depths. And you can actually solve this using the conjugate depths equation. A would be the height of the sluice gate opening. All right. Now, once you have A, you can find y1 using, there's a factor. All right. Just a second. Okay. Factor where you can times your height of opening, you will get depth 1. Now, y1, if you look at this, y1 is smaller than a lah, because due to contraction, right? So therefore, you can actually use this correction factor here. Now, this is pronounced as psi, all right? PSI is pronounced as psi, right? This symbol. This is the one, right? So depth of flow at vena contracta y1 is equal to psi times A, where psi is depth correction factor, which is actually between this number lah. Sometimes we could give you a number, which probably almost near this range, but don't worry about that. It's actually normally it's less than 1. When I say contracta, right, vena contracta, if you look at this, vena contracta is at the location where it has the smallest depth. When I say it's smallest depth, having constant Q, right, your velocity would be maximum. Because you said, because we have learned about, the continuity equation where Q equals to AV. All right. If your A is smallest, your V will be highest lah. All right, to get to achieve the continuity. So therefore, the minimum depth area or maximum flow velocity, immediate downstream of sluice gate is known as vena contracta. Okay, we'll look at this, all right, in the next in this equation later. All right. Now, this slide actually shows how you come to the equations that you are going to use to calculate discharge out of sluice gate or below the sluice gate. Now, using the Bernoulli's theorem, okay, we have the pressure term, we have the depth, we have the velocity term. So we are looking at the control section between 0 and 1. If you go back here, all right, this is the location of 0. And then this is, I'll put here 0, and this is the location 1. Comparing both sides, all right. You know, at this location here, right, the velocity goes down very small, almost 0. The pressure at this location, atmospheric pressure, is 0 as well. As well as location 1, the pressure, the hydrostatic pressure the pressure at the surface is zero as well. Okay, so but you have velocity, maximum velocity, right, at the Werner contractor there. So let's go back. So you have seen that this is zero because it's atmospheric pressure. This is zero as well. As I say, at the surface, the velocity is almost zero. Actually, you have learned about this equation in your orifice flow in fluid mechanics. If you still remember, uh, for a tank, the velocity in the tank is almost zero. So we only have y naught, y1, and v1 squared over 2g term left. Okay, so rearranging, that means I'm bringing y1 to the left. All right, I can write y naught minus y1 equals to v squared over 2g. Now rearranging this formula, right, because my intention is to get velocity or discharge. So I'm writing velocity as the subject of the equation. Um, so I have v equals to square root 2g y naught minus y1. Now, we know that Q is equal to AV, all right? So this is my V term, this is my A, and I have a coefficient of discharge. Basically, there is a correction term here due to the opening, all right, because it has some control due to the sluice gate, so you won't get exactly the Q. um, so you are introducing this coefficient of discharge. If you look at it, it's actually less than 1. You won't get greater than 1. If it's equal to 1, that means you get exactly equal to Q lah, right? um, Now, so these two equations are important where you want to find velocity as well as the discharge. Now, this discharge formula is also depends on whether your y1, if you still remember your y1 right here, is being submerged or not. Submerged means this y2 will control y1. Okay, it will go over, it will submerge over. All right. So now, depending on whether y1 submerged or not, you have to check y naught minus y1 compared to y2. If y naught minus y1 is larger than y2, then is y naught minus y1. Okay. Now, if y1 submerged completely, that means this is not this will not affect the flow already. So the rate of flow is only based on y naught minus y2. So when y naught minus y1 is less than y2 or equal to y2, then you will use this formula. So you have to be careful. But how in your um, final exam, if we have question on this, we are going to provide this set of equation. So don't worry. You just have to understand how to use all this. Let's look at one activity. We have a Swiss gate built in a rectangular channel with bottom width 1.5 meter. Normally, we have used this. We use uppercase B is the same. Flow and gate characteristics are given as y naught equals to 0.35, psi 0.63, the depth correction factor, and the discharge coefficient is 0.61. The height of gate opening is 0.12 meter. Now calculate the discharge under sluice gate if y2 is equal to 0.2. Now these are provided. You want to find, the question asks us to find discharge. So you are going to use this formula. Now what you have here is, do you have, is y1 given? So if, since y1 is not given, right? So you have to find y1 first. So we know that y1 is equal to uh, psi times a. So we are going to calculate y1 lah. Alright, which is psi times a. So you have 0.63 times 0.12. You have 0.0756. Then, which formula do you want to use? Remember, you have to check whether y0 minus y1 is greater than y2 or is less or equal to y2. So you have to check that. Y0 minus y1, since you have y1 already, right, is equal to 0.2744, which is greater than 0.2. So you can use the first equation lah, because this is not submerged, right? So Q equals to CD AB 2G square root 2G y0 minus y1. So you just substitute them. Okay. All right then. Um, so if you look at this, right, basically this, about on, actually on the topic of weir, spillway weir, it's all about application of formula, and you got to do some design when we are coming into the topic of scaling basin. So basically, this is the application of, you have learned about this equation, you apply them. Just list out what are the variables, and then you can, try to use, to try to find out how, which are available and which parameters or variables that you have to find out. The same thing for activity 5.2. I'm just going to go through because it's the same, almost similar question. Is given the width of the channel, the depth behind the sluice gate, and then you have the depth correction factor, the discharge coefficient, the height of gate opening, the depth, the downstream depth of further down, further downstream. All right. So this downstream depth is actually downstream of the sluice gate. Is y1. So y1 is equal to psi times a. You have this. You check the condition of control. See whether it's greater or smaller than y2. If it's smaller, then this is submerged case, so it's not influenced by y1 anymore. So you have y0 minus y2. Okay, so there are two cases. Activity 5.1, you are using the unsubmerged case. This one is the submerged case. All right. Straightforward, eh? For activity 5.3, right? If you look at this, right, the gate opening is given. Okay. Either you want to use the gate opening or not, it depends. Okay. Sometimes we tend to give you more information, but you not necessary you have to use them all. You have a sluice gate. The width of the channel is 1.5 meter. The B. Uniform depth y0 is 0.3 meter. That means behind the gate lah. Discharge coefficient 0.605. So in this case, right, y1 is given. Calculate y2. If you still remember in chapter 4, hydraulic jump, we will use the conjugate depth equation. That means we have y2 over y1 over y2 equals to half. All right, and then you have 1 plus if I'm not mistaken. All right. I think, yeah, okay. I think I might have some error in this formula. Okay, now, you can calculate your depth of y2, all right, using this conjugate depth equation, all right. So, however, if you look at this equation, right, you need to find fruit number of the upstream flow. How are you going to find fruit number? Do you have velocity here? Remember, we have learned about the formula of velocity here. You have y naught and y1 right in that equation. So you can find your v1 already. After you find your v1, you can find your Fred number already. Okay, so your Fred number is, v1 square root gy1. Alright, so therefore, oh, it's -1. Alright, therefore you have, V, you calculate V1 using that expression, all right, given. So once you find your V1, you can find fruit number already using V square root or divided by square root GY. This is supercritical. It's greater than 1, right? It's supercritical. And of course, if there's hydrate jump, then you can use this equation, all right? And fruit, when you are using this equation, right, fruit number is always the fruit upstream. Fruit number is always supercritical. That means it must be greater than 1 lah. So therefore, you have you can find your y2 using this. Oh, this is y2, y2 divided by y1. So therefore, you have, let's go back. This is actually y2, y1, -1. All right. Okay. Y2, you are using this conjugate depth equation. You substitute all the formula, all the values that you have obtained earlier, so you can find your y2. All right. Okay. Um, okay. Somebody raise your hand. Is it? Do you have question? Ada yang angkat tangan kan? Ada soalan ke? Okay, if you don't have question, then I'll proceed. Now, once you have y2, right? Before we calculate, we find out about this rate of flow going through this sluice gate. We need to establish the condition whether it is submerged or not. So you need to find y0 minus y1 and compare it with y2. So y0 minus y1 is equal to 0.11, which is less than y2. So it is being submerged. So therefore, you have to use y0 minus y2 formula. So therefore, you have 0. You substitute the discharge coefficient, the height of gate opening, the width of a channel, and then y0 minus y2 lah. All right. So therefore, your Q is 0.1529. Now, this is very straightforward for flow under sluice gate. Just substitute the formula. You apply the formula lah, provided. Okay, let's look at spillway. Now, there's not much calculation involved in our spillway, all right? Basically, there's none. We're just going through theory. We have further calculation in the topic under the topic of weir. Now, the term spillway, spill. So therefore, it is a way where water spill out. Okay, you provide a way where water spill out. So spillway is built in a reservoir to allow flow of water to safely move downstream. Now, when you build a dam, right? Okay, when you build a dam, you normally consider the depth behind the dam, because you consider the pressure, all right, towards this structure, the dam structure here. Um, Now, if the depth of flow behind the dam is too high, the pressure increases behind the dam. Then there's a risk of this structure being overturned. All right, being overturned. So therefore, you want to maintain the depth behind the dam. So therefore, you have this spillway where you allow water to flow out to safely downstream. So uh, to make sure the dam structure is safe. Now, the best design would be the OG spillway, where you have a smooth uh, crest of the spillway. Um, Now, this is a structure of a spillway. This is, the spillway where, when water raise rise up, to a certain height, it will spill out. Okay, spill out down to this stealing basin. Okay. You can't see it because it's being inundated. It's being submerged, all the structures down there. So this is the spillway. Because you have water gush down with high velocity, it will actually erode this location. So therefore, you have spillway, right? You have all these chute blocks and buffer blocks to reduce the energy of the water. This is OG spillway. There's a design here. You are going to learn this further either in your elective courses or in your master subject lah, where you can learn specifically on how you design them. Okay, I'm just going to go through. You can read this on yourself lah, by yourself, right? Now let's look at the third topic. I'm just going to stop in the middle of weir because I don't want to go uh, through too much in a day. So now weir is actually an overflow structure built across an open channel to measure rate of flow. You have river, right? It's built across it, so you can measure flow rate lah across the channel or river, natural channel, man-made or natural channel. Uh, is simple and reliable method. Okay, this is when we look at the longitudinal section, not across, longitudinal. You'll see this structure here. The height of the weir is, we are going to use P, is denoted by P. The thickness of the water measured above the crest of the weir is denoted by H subscript 1. Okay. Q is Q lah. Now, this is the nap. Actually, this thickness of the nap, right? If you have the thickness of the weir, okay, if is equal or greater than 60% of the thickness of the nap, then this would be considered as broad crested. So this is basically we are going to learn about sharp crested weir lah in this topic. Now, weir can be classified into various types based on the width of the crest and opening of weir. Now, if we look at the width of the crest, it can be classified as broad or sharp. When the weir has broad crested, or can be classified as broad crested when the thickness of the crest is more than 60% of the nap thickness. You have look at what is nap. This is a nap, right? Now, if we look at opening of weir, we can also classify the weir into rectangular, trapezoidal, or triangular notch. For example, This is a triangular notch. This is a rectangular. All this rectangular. This is a trapezoidal notch. Okay. Weir can also be categorized as submerged or non-submerged. Submerged means is being inundated lah. All right. For example, like broad crested case, right? Or non-submerged. That means it is not being inundated. The whole weir is not being inundated. Uh, all right. This is not submerged. This is submerged. Okay, submerged cases. So you have plate weirs. These are sharp crested, sharp crested. This is considered sharp as well. This is broad crested. Okay, because if you look at this, right, the thickness of this crest, right, is actually uh, more than 60% of the thickness of the nap. Okay, we have V-notch, suppressed, contracted, and Chipolliti. Well, this is a trapezoidal notch, but since the side slope has 1 to 4, it is specifically known as Chipolliti due to the side slope. If not, you can actually consider it as trapezoidal notch as well. Suppress means, okay, both side, there's no contraction at both sides. If it's being contracted, this is contracted at both sides. At certain cases, you can see it is being contracted at one side only, either left or right. Okay. So we are going to look at, a few types of weir: rectangular, triangular, and also trapezoidal weir. It's very simple. Now, rectangular weir are divided into suppressed and contracted. A weir is suppressed when the weir opening spans the full width of a channel. That means the weir opening has the same width as the width of the channel. That means it's not being contracted. That's why it's suppressed. Now, discharge over a sharp crested, fully ventilated and free-flowing suppressed weir is given as this formula. Now, how do they come up with this formula? Of course, they did. Researcher have gone through, dimensional analysis as well as experimental work. So they come out with this. When you are working on your master's and PhD research later, you will also come out with um, various formula or equation which is used in certain condition that you have prescribed lah. All right. So this is one of the case lah, where one of the researchers introduced this equation as well. But this is commonly used. Now, as you know, CD is the coefficient of discharge. Sometimes in the question will give you straightforward the value of CD. Sometimes will give you CV and CC, so you have to multiply them to get CD. Sometimes, will give you H1P and ask you to find CD. CD is not given, but you need to, but H1 and P are available. So you can find CD using Rebound Formula lah. All right. Let's go back. So the formula for discharge over rectangular weir. Suppressed rectangular weir is equal to 2/3 CD square root of 2G L times H to the power of 3/2. H1 is the height of the water measured from the crest of the weir to the free surface. L is actually the width of the weir opening. That L is the width of weir. It should be equal to the, if it's a press, it should be equal to the width of the channel lah. All right. So you have the Rebound formula, which is based on, the ratio of H 1 over P. So depending on, which range your H1 over P is, so you have, certain discharge coefficient where you can use. Okay, H1, okay, P, and then, okay. For this case, right, when the discharge coefficient, when the ratio of H1 over P is between 5 and 20, the CD actually has a smooth transition lah. You can actually, this is the case, you can actually do linear interpolation between 520 and 1.1 to 1.15 lah. All right. There's actually, I actually come out with this expression from a chart, okay, to help you lah, to ease you. If so, it's easier for you. You don't have to read the chart. You just use this equation here. Let's look at one example now. In this case, right, activity 5.4, we also have rectangular and trapezoidal. So we are not going to solve for triangular and trapezoidal yet. We are only will be looking at the rectangular weir. So we have a sharp crested weir installed in the rectangular channel. Discharging flow under a head of 0.2 meter. So this is H1, and discharge coefficient of 0.6. Calculate the discharge if the following weir is used. So we're just going to use this because we haven't learned about the formula for triangular and also trapezoidal yet. So look at this. You list out what are the variables provided. For example, in this case, you already have the head above the crest, which is 0.2 meter, discharge coefficient 0.6, and then the width of the weir, which is L, is equal to 1 meter. So basically, you are substituting all the known variables. So you can solve it directly. Okay. I'm not going to go through this yet. Okay. Maybe I'll just keep this. I'll go to triangular first. Okay. Now, just now you have look at, the formula for rectangular, which is 2 over 2/3, right? CD square root 2GH to the power of, if you look at this, is 3 over 2 lah. Okay. This one times L. So in this case, it involves triangular weir. Here's the thing. Now, how do you distinguish between rectangular and triangular weir formula? For triangular weir, you don't have L because there's no L. All right. If you have L only the top surface, well, it depends on the height. Okay, height of water. So basically, you don't have the width of the opening, so there's no L. But you have theta. All right, you have theta. So you can actually recognize this formula is actually for triangular. As compared to the previous formula, you have L. All right. So similarly, you have discharge is dependent on the discharge coefficient as well as the head of water of flow above the crest. And then you have in triangular case, you have theta over theta lah, all right, which is the the opening, all right, of the triangular weir. Okay, so don't worry about this. Sometimes we'll provide the discharge coefficient, not necessarily exactly 0.58. Right, this is just one case. When you are doing a research later, you'll with different condition, you'll get different coefficient of discharge. This is for a certain condition lah, which is not stated here. Um, be careful of the constants that are used. Okay. So basically, if you look at activity 5.7, right, it asks you to calculate discharge or flow through a triangular notch with vertex angle 60. So you have 60 degree and a head of 0.5 meter. Assume coefficient of discharge should be 0.58. So again, you substitute all the known values, right? You can find your Q. As simple as that. Um, okay, and then I'm going to go to trapezoidal weir. Okay, here's the thing. How are you going to distinguish between rectangular, triangular, and trapezoidal weir? Here's the thing. For trapezoidal, you have L and you have, theta. So if you look at that, okay, you have this. So you can easily recognize which formula you should be using for the three types of weir. Okay. Just now if you remember for the triangular, right, this vertex angle here is theta. In the formula is theta divided by 2. For the trapezoidal, it's actually this theta already represents half of your theta. Uh, if you consider this, if you combine these two triangular, right, it actually come out to one triangular weir. So this is actually represents your theta divided by 2 in the case of triangular weir. Okay, there's a similarity. Okay, if you here's the thing. You can actually combine this formula and the formula for rectangular weir. Combine them, you can actually get exactly the trapezoidal weir. Here you see, you factor this is if you open them up, you get 8 divided by 15 here. All right. So if you go back, this is 8 divided by 15. All right. So this is actually the combination lah, all right, of the two formula. You'll get back to this trapezoidal weir. Similarly, if you look at the question, you just need to try it out so that you understand how to substitute where is where. For example, how do you get theta and things like that. All right. Now before that, remember we have looked at this Chipoletti weir where the side slope is 1 to 4. Alright, so discharge through Chipoletti weir is given as this. This is similar as your rectangular weir formula. So you have CD equals to 0.63. This is also specifically for certain case situation. So you can use this equation. But I don't mind if you use this, uh, if you use the trapezoidal equation, it doesn't matter. All right. However, in this case, because it's Chipoletti weir, right? So you can use this simplified weir formula. All right. So because it's given, the side is 1 to 4. All right. Um, all right. Of course, you have to find your own data lah, because the site is given. We have been through this a lot in chapter 2 and 3. How to find the slope, the side slope uh, of trapezoidal or triangular. Okay, I'm not going to go through this today because it will be too much for you. What time already? No? Oh, it's still early. However, I think um, let's see whether then I think I'll just finish this up lah. All right. Okay. I think we stop here. We have okay. You can try this out. You can actually help me check whether my calculation is correct or not. Okay, go through all. I'm sure you can detect some error. Okay, because sometimes I just copy paste my equation, my formula, right? So I might make mistakes as well. Um, this is since you have H and P, right? H1 and P, you can use Rebound Formula to find CD in this case. Surprise, that means you have L. Okay, so you this is using Rebound Formula. Try it out. Okay. I didn't show you step by step because it's more on you list out all the known variables, you apply the equation, and you can get the discharge already. Okay. Let's look at contracted weir. Here, when it says contracted, right, you are going to have effective length because when you are contracted, right, this is from front view or cross section across the channel, front view. Okay, this is front view, but this view is from the top. If you're looking from the top, okay, the flow. This is the direction of the flow. So there's a correction factor where you need to find the effective length, LE. Okay. For suppress, weir, LE is equal to L. For contracted, okay, you need to find LE. This is when it's contracted at one side, and regardless of left or right, okay, but it's one side. This is contracted at both sides. So you have n equals to 2. All right, you have n equals to 1 here. Okay, so these cases. Okay. Okay, here's the thing. You see, this formula is exactly the same as your rectangular weir, except, well, it doesn't matter. You can use LE also for rectangular weir. Surprise, rectangular weir. You can use LE because you see, LE is L minus 0.1 n times HE. If your n is 0 for suppressed case where you don't have contraction, right? LE is equal to L. Okay? So however, if it is contracted, that means you have some effect due to the contraction. So you substitute. If it's one contraction at one side, then your n is equal to 1. If both sides are being contracted, so your n is equal to 2. So you need to find LA. So basically, what I'm saying here is you can just, use one equation, okay? Since, you get back your LE equals to L if it's a price when n is equal to 0 lah. When this is n equals to 0, okay? Um, Now, so this is basically the rectangular equation that you have learned earlier lah, except that you have to consider for the construction using by considering the effective length. This is another formula where you can find discharge coefficient of discharge using the Basin formula. Well, you might ask me, when are you going to use Basin, Rebound, and things like that? It depends on the question. If it's asked you to use Basin formula, then you use Basin. If not, you can use, you can choose to use whichever equation or you want. But if the coefficient of discharge is provided, you basically just use the coefficient straight away. Okay?
Doctor,
Yes.
I want to ask about for this one, the CD we can use for the previous one or not?
Mm, it actually depends on the question. Well, if the question gives you a CD, then you use that CD. If not, you can use it, you can use Rebound formula or you can use Basin formula. Okay,
Oh, so both formula can use
can use.
So
If the
both
question
formula can use
spec- If the question
Okay, thank you.
specifically use Basin, then you have to use Basin formula to find CD. Clear? Maksud saya kat sini ialah boleh guna
Clear.
mana-mana formula. Okay. Kalau soalan dah beri CD, tak payahlah guna Basin ataupun Rebound formula. Tapi kadang-kadang soalannya specifically suruh guna Basin formula untuk cari CD. Jadi kena guna Basin lah. Boleh Kalau disuruh guna Rebound, kena guna Rebound. Clear?
Clear. Thank you, doctor.
Okay, great. Okay, so you can, now in this case it's contracted at both sides. Well, this activity here use Basin. It's up to you if you want to use Basin or not. It's up to you. Of course, using different formula to find CD, you are not going to get the same Q. Remember that they actually are using Basin and Rebound or experiment. They are using different approximation or even different condition. So you are not going to get the same Q. Don't expect you are going to get the same Q. So in this case, right, you need to find, because it is contracted at both sides, you need to find the effective length. Okay. So basically you just substitute it lah. All right. You already find the CD, because I just talked about the Basin formula. So you can use the Basin lah to try to find the discharge, coefficient of discharge. All right. Okay. We have, completed Sluice gate, spillway, and also weir. Do you have any, question on this? On Wednesday, we are going to look at energy dissipator structure. This is all in the USBR's manual. So we are going to learn how to design the chute blocks, baffle blocks, and also the end sail on Wednesday. You can go through it lah. All right. So these are the different type. Apart from USBR Stirling Basin, you also have, other type of Stirling Basin, not necessarily from USBR only, but my slide only show USBR type Stirling Basin lah. There are so many type. There are 10 examples here. Okay, so we are going to look at this on Wednesday. So far, do you guys have any question? Please fill up your attendance. Okay. If you don't have any question, we'll continue next Wednesday. Is it okay, guys?
Okay, doctor.
All right. I'll see you next Wednesday.
Thank you,
Okay,
doctor.
doctor. Thank
Take care.
you.
Bye
Bye,
bye.
doctor.
Bye bye.
Thank you, doctor.
Thank
Thank
you.
you, doctor.
Thank you,
Thank you,
doctor.
doctor.
If you have
doctor.
question on the project, you can ask me too.
Okay, doctor.
Thank you, doctor.
Thank you.
Thank you, doctor.
You're welcome.
Doctor,
Yes.
will we learn about on which type of only design that type of wheel we will choose? We will choose.
Oh, you mean in practice, which type of weir you are going to choose? Is it? It depends. Actually, it depends on the site condition as well. Normally, typically, it's either the most common one would be either triangular or rectangular weir.
So if a question asks why did the company use rectangular type of knee, then we just say that it depends on the site situation lah.
Site condition, or
Site condition.
yeah, and then ease of measuring the flow. Normally it depends. Okay, normally if the flow is small, right, you probably want to consider triangular. If it's large
The
flow, you probably want to consider
um,
rectangular.
I see. What tapi what type or what value of flow that we can consider it as large?
Here's the thing, you look at the river, right? If you have
Uh-huh.
triangular notch, right, you will have water, you will block water from behind, from upstream, there will be too much, you because if you are using rectangular, you can actually measure larger flows.
I
Okay. It
see.
also depends on the width of the river. That's why I said you have to look at the condition of the site first. How, is it feasible to
Mm,
install triangular or rectangular weir?
uh, I see, I see. Thank you.
You're welcome, I said.
Doctor,
Yes.
for the
Because I
project,
think the final will have that question.
Oh, how do you know?
I think because uh nowadays the question are really hard, really
It's
open-ended
open-ended.
question.
Yes, yes.
Yeah, so need to know lah everything.
Okay.
Uh, thank
Don't worry
you.
lah. I'll help you guys out by giving some tips lah at the end. Okay. All right. Piriya, you have question, Piriya?
for the project,
About
doctor,
the project, yes.
we need to answer the questions only, or we need to add intro, conclusion, and literature review.
The second question, yes, you probably need to add something because you need to describe the site condition. Am I right?
Yes.
You also need to know, the existing condition before you
For the
suggest.
mitigation measures, is it? Or
Yes,
the
question two.
okay. Okay.
Okay.
So no need intro, conclusion, or no need, is it? For the
You
overall?
can you can do some intro too to question two.
Okay.
You want to explain about the study area and what is the problem you are investigating, right? You can do
Mm,
that.
okay.
Okay.
Alright, doctor. Thank you, doctor.
You're welcome. Okay. Ada lagi soalan? Mafira, Aizat, Syafiqah, Aidil,
Tak ada. Terima kasih,
Prince,
doktor.
Daniel. Okay. Okay,
Tak ada
Mafira.
doktor. Thank you.
Okay.
Doktor.
Okay.
Thank you,
Bye.
Doctor.
Bye.